Good afternoon, everyone, and welcome to the International Hub. I'm Professor Ksenia Chmutna. I'm the Director of the Institute of Advanced Studies here at Loughborough University. And it's my absolute pleasure to host our first Leicester IS and Loughborough IS jointly appointed fellow. And welcome to Loughborough. I believe you'll be spending time in Leicester as well. And our Leicester colleagues are here as well with us today, so welcome. As always at the IS, we're gathering here to listen about exciting research that is happening and to have a discussion and conversation about this. Just a couple of housekeeping rules. We are recording this presentation, but it's only the presentation that will be released as a podcast and on our YouTube channel. So when we have questions and answers, feel free to comment and have free discussion. That will not be released as a part of the recording. For those of you joining us online, please post your questions in the chat thingy on Teams, the technical term. We are monitoring Teams. For those of you in the room, you'll have time to ask questions, and of course, we will have lunch afterwards so we can continue the conversation. And I would like to invite Doan, who is hosting as Loughborough Academics, to introduce her, please.
Thank you very much for having us. Let me introduce our professor Anongnat. We call her the shortly Annie. She is from the Chulalongkorn University of Thailand. Chulalongkorn University is a flagship university of the Thailand. And Professor Annie from the chemical engineering department. And she was the former head of the chemical engineering department. And before the many degrees, she has been worked in the polymer science and polymer engineering, mainly for the energy storage technology and its application, particularly batteries. And among the main batteries, particularly the redox and metal air the batteries. And today, she's gonna talk about what she has done so far and what is the application of her the knowledge and her research on the polymer science. And by the way, I forgot that she jointly hosted by me from Urban School, but also the Jake Young from University of Leicester. So let's welcome again the Professor Annie. This is yours.
Thank you. So I like to talk about my work in the short time, 45 minutes. So first of all, I came from Thailand, and then I flew here to Heathrow for 12 hours flight, and then took like 3 trains to arrive here. So it took me around 21 hours from door to door. Yeah, but now I'm here and it's good. This house is good. And this is how my university looks like. Chulalongkorn University is in the center of Bangkok, and all those sky-rise building, you can see that. So we are like it's oasis in Bangkok. So you can visit us anytime. There are sky train and underground train just next to our university. So it's very comfortable to be here, to be in the university here. And I just did some homework to compare between 2 universities. Chulalongkorn University is a bit younger than Loughborough University, and we have like more students because we are comprehensive university. We have like all the discipline. But mostly are like undergrad. We have a smaller number of the master and PhD students. And for staff, we have around 3,900 academic staff. And for international students, we still have just only 4%, so it's still not a lot. We still welcome more international students. We have 19 faculties and also college and institute, so cover all the range of the knowledge. And we are in central Bangkok. And yeah, I think we can we have complementary between 2 universities. Like we work on several things. We have all the discipline to work on. And this is my background a little bit. I got my bachelor degree at Chulalongkorn University in material science, and then in polymer science. And then I went to University of Michigan, and I got my master and PhD on the macromolecular science engineering program. So it's polymer. And my work is that I try to study the that time is like how can we make the automotive parts that is better, lighter, and then stronger. So we just add the nanoparticle in the polymer, and then we have to understand like for the when it's flow, what is the behavior of the molten polymer uh, in the processing, and then after that how it crystallizes. So this is my work. I have to fabricate the equipment, and then after I got my PhD, that time I still think that I want more experience before I went back to Thailand. So I was researcher at the College of Pharmacy for a year to study the co-crystal formation of the medicine, and then when I went back, so I have to teach, and also because my background is polymer, so it's plastic. So I work on several things. That is like I try to work with the industry in Thailand. So usually we have like many small factory to produce packaging, film packaging, and also like many things. So that times like I work with post-harvest technologies to develop the bags that can extend the shelf life of fresh produce. And also another thing is that in Thailand, we also have like many big assembly factory to assemble. Like this one is the flip chip. It's a, we call it flexible circuit board that is like in your mobile phone, in your digital camera, and also in the cars. We use the flexible circuit board. And so the things that I try to work with the companies that I try to develop the adhesive that used here, that is like you can have the longer life of your circuit. So the equipment will be better. And then also the battery. Okay. So the first thing for the flexible circuit board, usually you can see that if it's the normal circuit board is all made from the metal. So when it's heated, so when it's like when you play games or like use it a lot, and it will be hot, right? You will feel that it's hot. Inside the temperature can go up to like 70 degrees Celsius. And when the temperature is increased, what happens is that the material will expand. And then when you stop using it, it will decrease, right? This will expand and then collapse like this. And then there is a stress. And when there are too much stress, the thing is, it will have the crack, due to the stress. So for the flexible circuit board, that is the difference between this. This one is the substrate. Usually it's a polymer, so it's have quite high degree of expansion. And then the chip is metal, and then we have the solid bump, and we have a chip that is metal. So we have smaller degree of expansion. So we have to match all this with the epoxy that is like try to release the stress when it is heat up and cool down like this. And then so I developed the formulation for this thing. And this is all the requirement that we have to have. Or that's okay. It's like we don't have to get into the detail. But this is usually the fact that occurs. And then that time the company said that okay, what we want is that we want to lower the time, the price, and also the number of heating process from 2 times to be 1 time and make it cheaper. So I worked with this company for like several years, have 2 US patent, and then also write one textbook that is not, it's not enjoyable to read, but it's okay. Yeah, and then so we developed the new formulation for the epoxy that can just finish in 1 heating process. So what does it mean is that we have to throw the epoxy in and then heat it, and then the thing is the bump. So it's the solder have to be molten first, and then the epoxy have to cure later. So we have to really understand the behavior of the epoxy and then work it that way. So this is the first one. And then, yeah, we got like pass everything and then can use it in the factory. And now the next one is that, you know, because we have many kind of things that we want to protect. Usually the packaging is like, is for protection, protecting the goods inside, right? Do you think we can use the same material to make packaging here? No, right? Because like for this one, the potato chip is like, it have oil. So if there are lots of oxygen, it will have some bad smell after we keep it for a while. And if there are too humid, the loss of moisture, it will not be crispy, right? Okay, so we need the package that can be a good barrier for water vapor and also oxygen. Okay, this one, the meat, if we keep it outside, it's like at a high temperature, so it will be rotten. It will be spoiled really fast. Even in the refrigerator, if there are, lots of oxygen, and then it's not cold enough, like in the refrigerator, it's 4 degrees Celsius, we can keep it just for several days because microorganisms can grow inside and it will be spoiled. So if we want to keep it for a long time, we don't want the oxygen to get inside the package. So the package for this one is like we want the oxygen barrier. For this one, for cookie is pretty much similar to this one, but mostly it's like usually we don't want it to be soft if it's a crispy one. So we don't want the moisture to get inside. So we want the water vapor moisture barrier for that one. Last one, the fruit. For the fruit, when we harvest it, it still use the oxygen. It still breathe in, use oxygen, and release the carbon dioxide and water vapor. And if we and also there are two kinds of fruit that is called like chimeteric and non-chimeteric. Chimeteric fruit is mean that when we harvest it, and for example banana, and then we keep it when it's still green, and we keep it for a while, it will start its cycle, right? Cycle by produce its own hormone. So it's ethylene gas that is a plant hormone. So when it produces, it will start to bright and then it will turn yellow. And then after that, it will be spoiled, rotten. That's all the cycle. And for another kind of fruit, it is non-chimeteric fruit. For example, orange. If you harvest it when it's still not mature, it will be taste like that. It won't change to be sweet from sour to sweet. So usually we have to pick it or harvest it when it's the right time. So this is non-chimeteric. So for the package for fresh produce, so we have to not only we have to let oxygen in. If there is no oxygen at all, like the plastic bag like this, if we put the banana in and then close it, banana inside will use all the oxygen. And after no more oxygen, what happened? It will start the anaerobic. It's like it's changed from using oxygen to be using don't use oxygen. So it will start the fermentation process. So what happened? You will have banana or mango that have weird smell and have the scent of like the alcohol a little bit. It's not good, right? So we don't want that. So this bag is not good for banana for sure. And so we need the bags that can let oxygen in, but not too much. If we want to extend the shelf life of fresh produce, for example, okay, for this one, this is my experience. It's like I got this from fresh market, and I keep it for 2 weeks, and it's still green, but I want to eat it. So I went to the convenience store and buy one banana, and then the yellow one, and I put it next together. over one night, the next day, this one start to turn yellow. And then, this is how we work on this thing, right? And, but if we want to keep it for a long time, one thing usually, for the factory, they put some chemical on this part and a little bit, and then it will slow down the process, the ripen process. Yeah. And so, as I told you that if we put it in just normal bags, like if it's really thick like this, there is not enough oxygen anymore. So the fermentation process will start and it's not good. And so the bags that I developed is that I try to let the oxygen in, but not too much. If the concentration of oxygen is 21%, like here in this room, the ripen process will be in the normal process. So we cannot, we can keep it for just the normal time. But if we want to extend the shelf life of fresh produce to export it to, maybe like from Thailand to UK, then we can keep the mango fresh for a month. So we need the oxygen level to be around 10 to 15%. And then also we have to let the water vapor that is come out from the fruit to go out. But if the carbon dioxide, if the water vapor go out too much, you will lose the weight. And then, it's like, it won't be fresh, right? So the level of the water vapor inside is have to be in the moderate level. And carbon dioxide, if there are too much of carbon dioxide inside the bags, like the normal bags like that, you will see the skin of the fruit to be a brown color a little bit, so it's not doesn't look nice. So we have to let the carbon dioxide out a little bit too. And also for the hemispheric fruit like banana, we need the bags have to be able to absorb the ethylene gas to make it bright slower. So this is how I developed the material. And then when we did it, it's like, okay, when I tell you the story, it's fun, but it's like when my students have to do all the experiment, it's not really fun because they have to do all this. And for mango, because usually in normal process it will be it ripe in around around 1 week. So if we keep in our bags that we develop, we want to try like 1 month. So usually they have to test it. My students have to test it every 7 days. Okay, so this is on the list. That's okay. We have to make sure that it's still firm. Or the flour change to how much change that is changed to be sugar. And also we have to make sure that the vitamin C is still inside, so the nutrition is still have to be the same. And lastly is sensory evaluation. So this one is not what my student tried, because she's not, when all my students didn't pass the how to say be the certified one. So it's like we have to ask people who have already passed be a certified person to test it, and then we can do everything here. And so for the mango here, this is the starting date, and then this is the peel, the pulp, and then the seed. And after 4 weeks, this is controlled. This is like the way that when the company export the mango, there will be around 1% of the rot fruit. But for when we use our bags, it's still all of them are still good. The nutrition is still good. Everything passed. So this is what we got. And also this thing, straw mushroom. I think some of you may know it, but some of you may not. Straw mushroom is the key ingredient for the tom yum goong. Tom kha gan. Tom yum goong, tom kha gan. But because we cannot grow it in UK, we cannot grow the straw mushroom in UK. So usually here, when you eat tom yum goong, you will have tom yum goong with different kind of mushroom. So the taste is not authentic. Usually come to Thailand. Yeah, so the taste will be better, much better, because it has its own scent and also the sweetness. It's usually in southern part of China, and then I think around Southeast Asia part we will have this. Uh, Usually, it have the shelf life is only 1 day. Usually, I cannot buy it at the supermarket. I have to go to the fresh market in the morning and then buy it. And when we go there, like in the morning, like at 7 or 8 o'clock, and then if we touch the back of the straw mushroom, it's hot. It's very hot because it releases lots of heat. It releases lots of heat. It releases lots of water. So that's why it's have like quite short life. And also it will produce the enzyme that it will destroy itself. So that's why it have shelf life around 1 day. What the cook do when they cannot cook it on that day? It's like if I go there to buy it and then I'm so busy, before the end of the day, I have to make it cook, like boil it or stir fry with some oil to make it cook so the enzyme won't work anymore. So I can keep it in the refrigerator, like the cooked one for 2-3 days. So this is like that time I got this request from the Thai restaurant in Germany, say that the owner, she wants to make the authentic tom yam goong. So he wants the company to export the straw mushroom to Germany, to Europe. So that's why we developed the bags that can keep it for 7 days here. And it's worked quite fine. We can keep it for 7 days. It's still fresh. The restaurant feel see the quality of the mushroom is still good. But finally, the price of the mushroom here, when they export to Europe, is still expensive, the same price as the normal mushroom here. So that's why they said that, okay, they still use the same mushroom, not use the straw mushroom. And for this one, is like I showed the papaya salad. That is also one Thai famous dish. We keep it in our bags that we develop, because when we chop the papaya, it's like the fruit have some injury. So when the cell injure, usually it have shorter life. So we try to see that how long can we keep it like this, like ready to eat food in the convenience store. So we pack it like 200 packs, and then we sell it in the how to say, it's a kind of farmer fair that is like we sell all the goods and also innovation from university. And then everyone say that it's still good for 2 weeks. So this is what we work on. And I say that, okay, this I spin off this company, but now it's like we just kind of inactive. And then the next one, okay, I joined I start to, I came to the UK like in 2015. It's like to join the Leaders in Innovation Fellowship Program, and it's really good. And then I really, recommend everyone to join this one. You can check it. I think it still have this program. And okay, after I joined that program, that's why I learned about how to be a startup, how to work with industry more than what I know before. And then I spin off the first company, Garden Fresh. And yeah, and then 2 years ago, Lord Cameron came to Thailand, and then so I have a chance to showcase my innovation, like the bags and also the mask here. So that's what I want to tell you more of right now. So this is the half-face respirator that is like we develop. My friends, my colleagues, and I, it's like I gather lots of people to come to work together for this thing, because during the COVID pandemic, we didn't have enough masks for medical workers. And then so that time, I think that first, I think I'm a polymer engineering, so I think I can do something. So that's why I try. And okay, so this is the situation, is that when we learn about COVID pandemic, usually many people compare it with Spanish flu. And then, when we start to see the zero patient in 2020, 2019, December 2019. And then during that time, so in Thailand is still okay. The situation is still okay until March that we start to have lockdown because we have like higher number of patients. And the problem is that 20 years ago in Thailand, we still produce the PPE, the coverall, but because the factory cannot compete the price with the goods from Vietnam and China, so they just stopped producing it for more than 15 years. And then, so we didn't have enough PPE. We cannot import that time because all the worlds, they have the same situation. And this is like, the situation get worse. And this is my friend who is the oral surgeon. And then one day she posts this photo and then she said that, even though, we're safe at home, but it's like they still have to work because they have to work with the patient that need their care, their surgery. So this is how they dress. It's like they use the raincoat that is made from polyethylene, the thin sheet, and then wear just the surgical mask because they didn't have the N95 mask at their hospital. So that's why I think that okay, I should do something. That time is like I serve as the associate dean for research affair at the Faculty of Engineering. So one thing is that I know that the assets of university is people. So at my faculty in engineering, we have 300 faculty members. So at least 300 expertise. And then all the university is like, we have more than 3,000 people. So we have all the expertise. So I think that, okay, I think I can do something. That's what I think. And then first thing first is like the Red Cross Society is like just start to have the first meeting. And then because they invite the dean of the Faculty of Engineering and also me as the associate dean. So I went there and then the whole room, there are only one polymer people. That is me. So, okay, I say that, okay, when they figure out everything, every process, how to get donation, how to procure all the PPE and everything, and who knows, how can we know that the quality of the PPE is good enough? So, okay, I don't know, but I can find it. So that translates, okay, after the meeting, I search all the standard. And then I just try to think, okay, what do we want? We want something to create pressure for fluid. So I asked professor in civil engineering, and he's so kind. He said that, okay, I will drive the car to the university. That at that moment to just try to set up the equipment. That this one is equivalent to test the soil. Yeah, this is the column, and then we put soil, and then we purge the water with different pressure, and then we know that how the soil is laid, the structure of the soil, and then we change it to put the cloth from coverall instead. And this is like at first we didn't have the synthetic blood, so we use only water first, and then we put the food color into it to know that okay, this color is not good because the water can pass through it. And fortunately, this professor, she's in chemical engineering, but her work is in biomedical engineering. So I asked her, for synthetic blood, we need these 7 chemicals. Do you have it? And then she said that, yes, she will prepare the synthetic blood for us. Yes, she just did it right away. And then I got the help from the postdoc that he worked with other professor, but I asked that professor that, could you help give me a hand or anyone to help her? And then we got it. Yeah. So, and then in 7 days, it's like from, for this one, when it worked, we know that the concept is work. So now we can design the better equipment to work faster and better. This one, he is a professor in civil engineering too. And then this is his postdoc. And when he knows that the concept is work, so he developed the new one so that his postdoc can test all the coverall that come to the Red Cross Society, the big batch, and then we cut it and then we test it. And then we got it in 7 days. And then we duplicate this equipment like a lot. So he can test a lot of coverall before we send it out to the hospital around the country. And then also when professor in pharmacy, in College of Pharmacy know about this, so she said that she want to help because on the standard is that we want to know whether the virus can pass through the coverall to not only the synthetic blood, but we want to know about the virus, so we test on that too. And also during that time, the private sector know that we didn't produce the coverall for more than 15 years, and then so they gathered together to try to make the fabric by or all the company that can do it, and then how to laminate it. So everyone worked together, and then we got the right one, and then we try to develop it, and we got the disposable coverall level 4, so it's the highest level that can protect people who wear it from virus and also the blood in 3 months. This is what we accomplished during that time. And then also next year, when we have enough coverall, the problem is that when people wear coverall in Thailand during daytime, it's 30 something degrees Celsius, so it's hot. And in May, it's like daytime can be 35 degrees Celsius, and the nurse and medical workers have to wear the coverall at least 3 to 4 hours when they visit the patient each room at the hospital. It's called that time we call hospital. We use the hotel to convert to be hospital to the patient that is like doesn't have the critical condition. This is how the nurse look like. So they are like so exhausted with the heat, and then so that time's like okay, the how to say, the doctor asked me that what can we do. So I said that okay, why don't we use the ice gel? This one, right? Just the gel that was like when we buy the meat or the cake, and then there is a gel that mixed between gel and water, and then we put it in the freezer, and then we got this one. So the hospital make more pocket to put more, and then they love it. They say that oh, it's good, but some doctors concerned about ice burn, because the pack is like the temperature is 0 degrees Celsius. If it touched our skin for a long time, because the nurse work all the time, they just forgot about themselves. So if ice burn occurs, what happened? So I changed from that gel pack that is like just temporary, and then I asked the alumni of my faculty. He has a factory to produce the paraffin. Paraffin is the long chain of carbon that is still liquid, and then it can change from solid to liquid in like temperature that we can choose like up to the how long of the polymer chain, and we choose the one that can change from solid to liquid at 21 degrees Celsius. So it means that people can wear it and feel the temperature around 21 degrees Celsius for 2-3 hours, and it's like it doesn't have problem with ice burn for sure. And this is how we work. And then I got lots of help from many companies, even my friend's company that make the packaging. So they pack it for us. And also many people make the vest and have lots of pocket, because so the nurse and doctor can just wear it, doesn't have to make the pocket by themselves. And this is how it looked like when we wear it. And we sell it out around 20,000 set of this vest and pack to hospital. And the last thing, okay, this one is a mask. This one, because we didn't have company to produce, the factory to produce the N95 mask in Thailand. We have lots of problems. So that time we gather people like my friend, my colleagues, and also my student, my former student, everyone, private sector, and then we work together to design. And then I got one designer from the big company that they lend one designer that, okay, work on this project. And then we got this. You can see that the idea is that if we wear N95, it will like hurt here, right? Because it's like very hard. This one got the design got from the idea from the scuba diving, that usually when we put the mask, we didn't feel hurt on the skin because it's soft silicone. And this part, we because my friend's factory, they produce the jar for the candies. So the idea is that if we close it like this and turn it like this, it's easy. And then everyone can put the filter on. This is like the quality the same as N95. Put on here, and then we close it, and then oops, and then done here, and then we can wear it every evening after work. We can just remove this part, and then we wash it by soap, like when we wash hand, and then we can destroy all the virus, right? So this is like washable, reusable mask that we develop. And we got an idea, okay, from here it's like from candy jar, this one from scuba diving, this one I got the help from the factory that produced the shoe lace. Yeah, they asked that, okay, they can do it. And then they did it right away for us. And then we make it. And yeah, this is how it looked when we wear it. We can see the face a little bit. So, people can communicate and see emotion. And yeah, he is the general, and also he's a doctor. So he's a soldier and doctor. And then he manage the hospital. So he just kind of take the photo, and then just told us that okay, it worked really fine. And then many people just say that it's good. And this is how we send it out to around 300 hospitals during that time by using the donation model. So it means that any people who want to help doctor just transfer money to us, and then we send it and then we ask each hospital, how much do you want? How many masks do you want? And then we send it out. So, we just send it out to everywhere. And yeah, we got the Good Design Award here. It's in Japan, right? Yeah, it's the Good Design Award is from Japan. And after COVID pandemic subsides, like what can we do with the mask that we still have? So we have the problem with the air pollution in the north of Thailand. So we just donate it to the north of Thailand. Yeah, we just send it out when there is a problem. So that is the thing that is like I try to gather the things that not only expertise that is important, but the team, the empathy that we try to understand, the user. And then we try to innovate something that is have to be sustainable. Because for this one, we got it. Also, the thing that we got this idea because that time we cannot produce this thing. We have to import it. So we cannot make a big mass like the big one, the N95 one is used a lot. So this one is smaller, so we can save the material. And okay, so this is how I know Dr. Dovan from the World Class University Consortium from British Council grant. And then we discuss on the Zoom meeting first, and then later when we can travel. So we visit many universities that time. But I didn't meet Dr. Dovan that time because I got COVID. During the trip. So it's like, okay, I stuck in the hotel that I cannot go there. And my colleagues went there to see him. Yeah. And also I work on I got the Frontiers Champions grants, a small grant to find the missing, that times like we try to see about Thailand's energy transition because we still have many gaps that we need to fill out. We have to learn about that. And then the last thing, I also work on the battery. And this is because there are many kinds of battery, but in my group is that I work with Professor Suratev, that is like my colleagues at Chulalongkorn University in chemical engineering, and he works on the battery like design develop the catalyst, develop the cathode. But for me, mostly because my background is polymer, so mostly I try to work on the separator that is also made from polymer, and a little bit of the encapsulation of the iodine in the zinc iodine battery. And so this kind of many kind of zinc battery that we work on. And so this is the work of my PhD student that she just defends for her PhD like last week. So now she's done. And yeah, and then so the first work that she tried to encapsulate the iodine in the coil cell of the zinc iodine battery, and it worked pretty good. It's like this one is like when we didn't use any of the material that she developed, and then she used the layer double hydroxide, and then you can see that the specific capacity is much better here, and the cooling efficiency is here, and this is her work. And then after this work, she still think that okay, I can do better. So she decided use the bismuth modify of this the layer double oxide, and you can see that for the specific capacity of this work is this one. Let me see. Okay, this one is much better than the other works, and even for her the first work of the works. Okay, so this is we try to encapsulate the iodine to make the coil cell of the batteries and work better. And then another thing is the separator. For separator, it's like we have the flow battery, zinc polyamide flow battery in the lab, in Professor Suratev's lab. And then I try to develop the separator. But this is what the work of my another PhD student who graduated last year. And yeah, and then he tried to make, the concept of polymers that we have to think that, okay, what can we do? Because for polymer, we can shape it. We can make pore size, how much of the, how big of the pore size, how much of the pores, we can control everything. So that is the good thing of polymer. The bad thing is that it's usually is not tolerate the high heat, so that is not a good thing, right? But for this kind of battery, we don't have to use it at the high temperature, so that's why it's okay. And then so we develop the separator, and then with the idea that we make a pore that is like small pore, and then and then we make sure that high proton can go through it, but triiodide ion cannot go through it. This is the concept, and then we got it work. It worked better than the Nafion, the commercial one. And this is another work of another student. This one is let me see, it's the zinc air battery. And for this one, we want to make the separator that is like, it's cheap, it's sustainable, we try to use the one that is like, have the cytosan, and then the PVA. And now for this one, you can see that for the just material is like, have the lifetime is quite short, and then it's longer when we add the molybdenum disulfide and also the cytosan here. That's what he tried to develop. And then his second work is that he wants to make it cheaper. Yeah, if it's good, if battery work well, but it's expensive, we can use it, right? We cannot sell it. Okay, so yeah, this is the porous PP, just the normal separator, and then we just, instead of make the whole separator from this material like this one, we just decided, okay, we use porous PP, and then we coat it with the layer of the material that we developed from the last paper. So this will be just the thin layer, and then we test it, and then you can see that it works much better and it's cheaper. Yeah. So okay, the last thing, so it's like all the works that I told you that I didn't work on by myself. I work with many people, and especially for the energy storage work is that we try to build up the ecosystem in Thailand. We got the grant to try to work between I can say that I'm a senior researcher now, right? I'm not young anymore. And then what we try to do is that we have to make sure that the young generation can grow up and can continue the good work, and they are much better than, my time, and then they have to work better. So that's why we try to make an ecosystem, and then we try to work from with everyone in, any country, because for the problem with the energy, it's not a problem for only in Thailand, but for everyone. And yeah, this is the group that we work together. It's we gather people that we have around right now. Only in this project is 22 researchers, and then we try to add more. We visit several universities, and then we ask to collaborate. And if you are interested in the work that we are doing, you can scan the QR code, or this is the website. We try to upload all the project and all the activity, like all the conference that and yeah, lastly, so I like to acknowledge all the funding and all my students, all the colleagues that work in, my life, that can be easy with them, and then I can do everything. So thank you very much.